Okay, welcome back once again. All right, the end of chapter 6, and they're breaking the periodic table down two ways. They're going to look at metals, nonmetals, and metalloids and where they are on the table and what their properties are. So, what do we have to know about metals, metalloids, stuff we learned in middle school? We have to know the properties, and we have to, properties, and we have to know the location on the table. And groups versus families, some of them have special names, so you have to know those. And in terms of what the difference is in terms of chemical versus physical properties. And I'm only going to briefly mention that because in the next unit we actually talk about chemical versus physical properties. So in other words, why they are placed the way they're placed on the periodic table, which we somewhat already know. Okay, first of all, properties of metals. So let's label this properties. Now, we'll discuss why they have these properties when we talk about bonding theory in chapter 12. But for now, you have to know that metals are shining. That's what they mean by luster. And they're good conductors of heat and electricity. That has to do with particle physics. But for now, you just have to know the property. They are malleable, which means that you can hammer them into different shapes without breaking them. And they are ductile, which means that they can be drawn out into tiny, long cylinders known as wires. Where are they on the periodic table? Glad you asked. Okay, we said on the periodic table that this right here represents break line between metals and nonmetals. And so we're going to find our metals over here to the left and below the break line. Boy, I really missed that line. And then above and to the right, we find our nonmetals. And then some of the elements along the break line are considered metalloids, or what they call semi-metals. Now, the definition of a semi-metal is that it has some properties that are metallic and some that are non-metallic, and most of them can be found, or most of the things along the break line are considered metalloids. In fact, let me see if I have them all. What are my metalloids? And again, it depends upon the definition of the scientist which ones are metalloids, because if you look at this chart, the yellow are the metalloids: boron, silicon, germanium, arsenic, antimony, tellurium, and astatine. But I've seen some charts where they're slightly different, and again, it depends upon the scientist. Some scientists believe that it has to be an equal amount of non-metal and metal properties to be considered a metalloid, and some are, well, even if you only have one property that's different. If you have all metallic and only one property that's non-metal, you're still considered a metalloid. So we're going to count these: boron, silicon, germanium, arsenic, antimony, tellurium, astatine. So let's go back to our blank periodic table. So those are our metalloids. All right, so what are the properties of a metalloid? Well, apparently we're going to get to nonmetals first. Nonmetals are dull, and again, that has to do with the bonding structure. We'll get into that in chapter 12. They are brittle, so if you hit them with a hammer, they break apart. They are poor conductors of heat and electricity. Do understand that everything conducts heat and electricity at least a little bit. But nonmetals tend to resist electrical energy, and they're what we call insulators. Now, metalloids have some metallic properties and some non-metallic properties. We already discussed that they are most of the elements along the break line. They are dull like nonmetals, but they're malleable like metals. So for instance, silicon can be hammered into sheets that we use for circuit boards and chip boards on computers. They are poor conductors of electricity unless they are contaminated by other compounds in a process they call doping, which means to contaminate something on purpose. And in that case, they become superconductors. So able to conduct electricity without much resistance, so they don't get particularly hot when they conduct electricity. Second way of classifying the periodic table is based upon periods and rows. And here's what they want you to know about it. All right, periods go from left to right across the table, and groups, in other words, a period is a row, and groups are the columns. And groups are sometimes called families. And I'll explain why in just a moment. So the first row going across from left to right, this is called the first period. And then the second row would be the second period, etc. Third row is the third period. Now what distinguishes the periods is that the row number is also the highest quantum energy number. So if an element is in period 4, that means that its highest energy electron will be in the fourth period. So the example they give you in the book is potassium, and we would say that potassium has an argon core, 4s1 configuration, so its highest energy electron is the 4s1. Whereas if we're dealing with zinc over here in column 12, it has an argon core, 4s2 3d10. Now its outermost electron is in d10, but its highest quantum energy level is 4 for period 4. Now the groups, the reason why they call them families is that they have the same outermost electron config. Same outermost electron configuration, which means they have the same chemistry, the same chemical properties. And we're going to get into chemical properties in the next chapter. Alright, so if I zoom back in on this, let's use purple, and let's erase some of this that's getting in our way. Alright. So everything in group 1 ends in an S1 configuration, so they have similar chemical properties. For instance, if sodium forms NaCl with chlorine, potassium's going to form KCl. They're going to have the same type of properties. Lithium is going to form LiCl. Use a different color here. In the second group, all the outermost electrons end in an S2 configuration. So if you are magnesium, you form a +2 charge and you get MgCl2. So we can predict the formula for calcium with chloride. It's going to have the same chemistry and produces the same type of formula, 2 chlorines for every calcium. And we said that with these families, if we're just focusing on the main groups, this would be P1, P2, P3, P4, P5, and P6. Okay, so again, groups are families of elements. They're in the same column. They all have the same outermost electron configuration, so therefore they have the same type of chemistry. And the last thing you have to know for the periodic table in Chapter 6 is some of the groups have special family names, and so they will want you to identify those names, so we will do that. Now, some of the groups do not have special names. We'll deal with that also. All right. So, group 1, these are called the alkaline metals. And group 2 are called the alkali earth metals. Three through 12 are called transition elements. And these right here in the F block, we're going to call the 4F lanthanides and the 5F actinides, or you can collectively call them whoa, I'm having eye pencil problems. We're going to collectively call them rare earth elements. Alright, some of them do not have special names. Group 13, for instance, starts with boron, and they just call group 13 the boron group. And group 14 starts with carbon, so they just call this the carbon group. Group 15 starts with nitrogen, so naturally we call them nicogens. I don't know why. And then oxygen has a special name called chalcogens. And 17, the fluorine column, that has a special name called halogens. And then the last group is your Mr. Noble gases. And that's it. That's it for Chapter 6. Chapter 10 is all about periodicity, how the periodic table is shaped to allow us to predict certain chemical and physical properties. But for now, that's it. So, thank you very much.